The cosmos is not silent, but it is incredibly good at keeping secrets. When we look up at the night sky, we see a static tapestry of light, but the reality is a dynamic, gravitational dance. For decades, astronomers have been trying to learn the steps of this dance, scanning the heavens to collect the faint whispers of distant worlds. We have been remarkably successful in some areas and completely blind in others. We have found planets that block their stars, light, known as transits. We have found planets that tug rhythmically on their suns, revealed through radial velocity. But a vast, silent majority of the universe's giant planets have remained effectively invisible. These are the worlds hidden in the blinding glare of their host stars, orbiting too far away to transit and moving too slowly to create a noticeable wobble. They are the ghosts of the galaxy, until now. A revolutionary new strategy has emerged from the summit of Mauna Kea in Hawaii, and it is fundamentally changing the game of exoplanet hunting. It is called OASIS, the Observing Accelerators with SCEEXAO Imaging Survey. This is not just a new instrument. It is a hybrid protocol that combines the exquisite precision of space-based cartography with the raw power of ground-based optics. By fusing data from the European Space Agency's Gaia mission with the Subaru Telescope's extreme adaptive optics, OASIS has begun to unveil a population of hidden giants that previous methods missed entirely. This is the story of how astronomers stopped searching blindly in the dark and started hunting with a treasure map. To truly understand the magnitude of the OASIS breakthrough, we must first appreciate the immense difficulty of the task at hand. This is the challenge of direct imaging. In the world of astronomy, direct imaging is considered the holy grail. Most methods we use to find planets are indirect. They give us numbers on a graph, a dip in brightness, or a shift in a spectrum. But direct imaging gives us actual photons from the planet itself. From these precious packets of light, we can analyze the planet's atmosphere, its temperature, and its chemical composition. It turns a statistical data point into a physical world. However, obtaining this image is one of the hardest technical challenges in science. Imagine standing in Times Square in New York City and trying to spot a single firefly buzzing next to a lighthouse located in Los Angeles. Now, add another layer of complexity. Imagine the lighthouse is blindingly bright, and you are trying to take a picture of that firefly through a turbulent ocean of air that distorts the image. That turbulent ocean is Earth's atmosphere. This is the reality of hunting exoplanets. Because planets are millions of times fainter than their stars, astronomers have historically been playing a game of extreme chance. They had to guess where to point their telescopes. They would target young stars, where planets are still hot and bright from their formation, and simply hope for the best. The success rate was abysmal, hovering around 1%. It was a blind search strategy, akin to fishing in a vast empty ocean without a fish finder. The result of this inefficiency was an exoplanet gap. We knew about hot Jupiters, the massive gas giants hugging their stars tightly. We knew about small rocky worlds. But the wide-orbit giants, the cousins of our own Jupiter and Saturn circling in the frozen outer reaches, remained largely ghost stories. We knew they should be there. Our models predicted them, but we could not see them. This is where the genius of the OASIS protocol comes into play. It refuses to rely on just one method. Instead, it is a hybrid strategy, marrying two very different branches of astronomy, astrometry and high-contrast imaging. The hunt begins not on the ground, but in the silent vacuum of space. The first half of this hybrid beast is the treasure map, provided by the European Space Agency's Gaia mission and its predecessor, Hipparcos. For years, Gaia has been mapping the positions of over 1 billion stars with unparalleled precision. We often think of stars as fixed points, nailed to the celestial sphere, but they are not. They move, they drift through the galaxy in predictable paths, but if a star has a massive companion, a hidden giant planet, or a brown dwarf, that companion will exert a gravitational pull. As the planet swings around its wide orbit, it gently tugs the star off its straight-line path. This tug is minuscule. It does not look like the rapid back-and-forth wobble detected by radial velocity methods. Instead, it manifests as a slow, subtle acceleration. By combining Hipparcos data from the 1990s with modern Gaia data, astronomers can see a timeline of motion spanning decades. They can see that a star is curving slightly through space, pulled by an unseen hand. This acceleration is the X on the treasure map. It tells astronomers exactly which stars are hiding heavy companions, eliminating the guesswork that plagued previous surveys. Once the target is identified by this space-based data, the baton is passed to Earth, specifically to the 8.2-meter Subaru Telescope atop Mauna Kea. Knowing where to look is only half the battle. You still have to see the target through the atmospheric turbulence we discussed earlier. For this, OASIS utilizes the Subaru Coronagraphic Extreme Adaptive Optics System, or SCEXAO. This system is a technological marvel. It addresses the atmospheric distortion problem using a deformable mirror. This is a mirror that can physically change its shape 2,000 times per second. It ripples and shifts in real time to counteract the blurring caused by Earth's atmosphere. It effectively deletes the twinkling of the stars, restoring the sharpness of space-based views while keeping the light-gathering power of a massive ground-based telescope. Combined with a coronagraph, a device that physically blocks the blinding light of the central star, SCEEXAO creates a zone of artificial darkness around the star. In this dark zone, the faint light of the hidden planet, previously lost in the glare, can finally pop into view. In late 2025, the OASIS team, led by principal investigator Thane Curry of the University of Texas at San Antonio, announced their first confirmed kills. The results were nothing short of spectacular, validating the hybrid method instantly. The first major trophy of this hunt was a world named HIP 54515b, located 275 light-years away in the constellation Leo. The star HIP 54515 showed a suspicious curve in its motion through the galaxy. The Gaia data was screaming that something massive was pulling on it. When the Subaru Telescope turned its SCEXAO toward the star, the hidden world was revealed. It is a colossus. HIP 54515b is a gas giant with a mass nearly 18 times that of Jupiter. But what makes this planet fascinating is its architecture. It orbits its star at a distance of 25 astronomical units. To put that in perspective, in our own solar system, that would place it roughly where Neptune sits. This presents a significant anomaly. In our system, Neptune is an ice giant, relatively small compared to Jupiter. But HIP 54515b is at Neptune's distance, yet is 18 times heavier than Jupiter. This discovery challenges our standard models of planetary formation, specifically the theory of core accretion. Core accretion suggests it should be very difficult to form such massive planets so far out, where the material in the protoplanetary disk is sparse and moves slowly. The existence of HIP 54515b suggests that the outer reaches of planetary systems are far more diverse and populated than we dared to dream. It forces theorists back to their chalkboards to consider alternative formation methods, such as gravitational instability, where the disk collapses rapidly under its own weight. The second discovery, designated HIP 71618b, might be even more critical for the future of astronomy, though for a different reason. This object is a brown dwarf. Brown dwarfs are often called failed stars. They are intermediate objects, bridging the gap between the largest gas giant planets and the smallest stars. While brown dwarfs are scientifically interesting on their own, HIP 71618b serves a higher purpose. It has become the perfect test subject for NASA's upcoming Nancy Grace Roman Space Telescope. The Roman Telescope, scheduled for launch later this decade, will carry a next-generation coronagraph instrument designed to image Earth-like planets. This is high-stakes technology. To work, it needs to test its instruments on known, faint targets orbiting bright stars. Before OASIS, we did not have a good target that met all the necessary criteria. We were essentially building a camera without a test chart. HIP 71618b checks every box. It is the Rosetta Stone that will help us learn how to read the light of Earth 2.0. By training the Roman Telescope on this brown dwarf, engineers can calibrate the instruments that will one day search for life. The success of the OASIS protocol represents a paradigm shift in astronomy. We are moving from the era of discovery by luck to the era of discovery by design. This shift brings three massive advantages. First, efficiency over volume. Traditional direct imaging surveys might observe 100 stars just to find one planet. It was a massive expenditure of telescope time, which is one of the most expensive resources in science. OASIS selects only the stars that show the telltale gravitational tug. This pushes the detection efficiency from 1% toward nearly 100% for the selected targets. It transforms the search from a gamble into an investment. Second, we are bridging the gap in our knowledge of planetary architecture. We have thoroughly explored the inner regions of solar systems using transits and the intermediate regions using radial velocity. OASIS opens the door to the solar system scale, planets orbiting at 5, 10, 20, or 50 astronomical units. These are the cold giants. They act as the shepherds of planetary systems, shaping the orbits of comets and asteroids, and potentially protecting inner, habitable worlds from bombardment. Understanding them is key to understanding how our own solar system formed. Third, and finally, it helps us understand formation physics. The existence of massive planets at wide separations forces us to question how planets are born. Did these planets form closer to the star and get kicked out? Or did they form in situ? OASIS provides the data points needed to solve this riddle. The future of this research is bright. The OASIS protocol is currently surveying dozens of other candidate systems. The acceleration map provided by Gaia suggests that hundreds of these hidden giants are waiting to be photographed. As we look forward, the synergy between ground and space will only tighten. The upcoming Roman Space Telescope will not just test technology, it will likely use the OASIS protocol to select its own targets, creating a feedback loop of discovery. We are entering a golden age of exoplanetary cartography. We are no longer just counting shadows or wobbles on a graph. Thanks to the hybrid hunt of OASIS, we are taking portraits of the family members of the cosmos that have eluded us for so long. The giants are no longer hidden, they are just waiting for us to look in the right place.